wait for the microphone. This section here is called the physical structure of atoms. Okay, what do atoms look like? Again, to be very clear, you can't look at an atom. To look at something means you have to bounce light off of it, right? And atoms are smaller than the wavelength of visible light.
What slide is that?
It's slide 14. Yeah, if you're following at the PowerPoint, you're probably learning that I don't go in exact order. I never do because it doesn't fit. So I go in my order. But anyways, and I usually give you guys the PowerPoints unedited. Like I just give you the whole PowerPoint, and I will occasionally edit the PowerPoints to fit what I want to do.
Because I'm blind.
That's great. No, please, I love that. I love that you guys are doing that. But just know that I won't ever go in exact order. If you don't have the PowerPoint in front of you, it seems more smooth and fluid. But when you do, you're like, oh, where'd he go? Okay, so we're going to go down to the physical structure of atoms. Okay, so let's remind ourselves a couple of things. There have been several times in history, all of them before, let's say, the 1920s. Okay, so our modern picture of an atom is circa 1911. Okay, we've had this modern picture for 111 years, okay? But Ernst Rutherford, they spell it Ernest, his name is Ernst. Ernst Rutherford, in 1911, does an experiment with a alpha particle gun, okay? And remember, Neil deGrasse Tyson explained it, I've explained it before too. He shoots a stream of particles at a very thin sheet of gold foil, okay? Expecting that either what he kind of expected is that all of the particles would be deflected. It's a sheet of gold foil after all. Gold is pretty dense. Wouldn't you expect that if you shoot particles at a sheet of something solid, they would bounce off? Because every time I throw a ball at a wall, it bounces off of that wall. Okay, that was the naive expectation, right? By the way, in science, they love it. Scientists absolutely love it when they do an experiment and you get a completely different result than you expected, okay? Something interesting and new that doesn't fit your data. And now you got to go, well, I have to explain that now, right? That's where science makes progress. Okay, good. But 1911 he does this. It was actually his graduate student. I forget the name, but his graduate student does this. But the point is he gets the credit for it. And he expects that you shoot particles at gold foil, they bounce off and they hit the detector coming back this way, right? All of them, okay? But maybe you guys remember what he actually found was that almost all of the particles shot right through the gold foil to the detector behind the foil. And every once in a while, a particle would bounce directly back, almost a straight line back towards the alpha particle ray gun and hit the detector right in that area, okay? Which is hugely counter to what they thought. Remember, they didn't know that atoms had a hard center, a dense center and orbiting electrons. They kind of just thought that atoms were a big bag of particles, right? They called it the plum pudding model of an atom, where they thought that, atoms are just a bag of particles, and they're all positive and negative charges because we knew about electric charge, but we didn't know where they were situated in the atom, okay? Now we've got a very good idea, and that is primarily because of Ernst Rutherford's experiment in 1911. So he shows that the atoms consist of a dense and positively charged nucleus surrounded by a cloud of negatively charged electrons. There were some problems with Ernst Rutherford's model, namely that he thought the electrons were in actual orbit and any possible distance from the atom, kind of like planets can be any possible distance from the sun and orbit the sun. The problem is that when a electron moves around in its orbit, the moving electron is disturbing the electric and magnetic field and should radiate photons, okay? But they don't in the way that they should in the way that they should have if his model was true. If his model was true, all electrons should orbit, radiate away photons, and spiral into the nucleus, annihilating themselves. Okay? But as you can see, we are here. We have not blown up. We have not annihilated. All of our atoms are still present, right? And so they didn't think that that was the case. They knew instantly when he built his model of the atom, when he decided what atoms looked like, they go, that can't be right. Okay, so it took a couple more years. Two people, importantly, they mentioned Niels Bohr here, but later there's another name that's going to pop up, Max Planck. Max Planck did the mathematics side of it, Niels Bohr did the physics side of it, but they came to the agreement that, and I'll just read what Niels Bohr came to find out. They showed that electrons, this is going to be super important to what we are going to learn about. Electrons can only exist at very specific energy levels. Electrons can only be this distance or this distance. They cannot be any distance in between those shells. They exist in shells, okay, shell levels. That's why when I drew it, I talked about the electrons being at individual, discrete, quantized distances from the nucleus, okay? Niels Bohr said that should be the case, and Max Planck did the calculations to prove it, okay? That's extremely important. Electrons do orbit the atoms, but they have specific distances that they cannot change from without either, remember this, right, absorbing a photon and moving up a level, or emitting a photon and moving down a level. That was what we had kind of hinted to earlier with the ball and the hill analogy. These orbits or shells, and this is now maybe more than you want, and I bet this confused you. These orbits or shells are actually made up of different what are called suborbitals or orbitals, each of which accommodate 2 and only 2 electrons. So I'm going to show you the picture of what we call an orbital, and then I'm going to never talk about it again, okay? Because you do not need it for radiography, all right? So this is what we call an orbital, okay? So here's the picture you probably have, okay? Electrons sit at specific distances here, and here, and here, and here, okay? This is the picture we use for radiography, but it's not right, okay? It works for radiography, it worked for Niels Bohr, but it's not exactly right, okay? This is the true arrangement of electrons and atoms. So in the center here will be a nucleus. They're not showing you the nucleus. And depending on how many electrons an atom has, the electrons will take the electron orbitals, which I'll explain in a moment, will take different shapes, okay? And the idea here is that you can't tell me where the electron exactly is. You can only say the electron is going to be somewhere within this space. So the s orbital is a sphere, okay? You can't tell if the s orbital is the shape of the electron orbital around the atom, the electron is going to be found somewhere in that space, but you can't tell me exactly where. You can only say there's a high likelihood of it being close to the nucleus, there's a low likelihood of it being far away, and you can't tell me exactly where it's going to be. That's what quantum physics does, is it says you can't tell me where something is, you can only tell me what the likelihood of finding it in a specific spot is, okay? So that's orbitals, okay? And orbitals have funny shapes. There's s orbitals that are pretty straightforward. There's d orbitals that look like a dumbbell with a ring around it. And so if your atom has an orbital shape of the d orbital, then your electrons are going to be found somewhere in this green area, okay? You can't tell me where exactly. You can only tell me it's going to be in that area, and then we do an experiment, locate the electron, there it is, okay? If you've studied anything about physics, this is what's called a wave function, okay? And I won't tell you more than that. All right, because we don't use it for radiography, okay? The Bohr model, this model is called the Bohr model of the atom, showing the electrons arranged in shells is sufficient to illustrate all of the concepts we need to understand for physics and radiography, okay? So we don't need to understand quantum mechanics. We don't need to understand orbitals because we don't use them. We're not doing chemistry, we're doing basic physics, and we're not doing quantum physics, okay? So we do not need orbitals. Read them in the book, go, that's interesting, and then move on, okay? I promise you, because it won't help you, okay? So that's important. All right, Bohr's model. Bohr's model agrees with Rutherford's, by the way. Bohr's model says, yeah, there's a nucleus, there's all the protons and neutrons, okay? There's all the electrons. They orbit around the nucleus at some distance from the nucleus, okay? By the way, can anyone help us remember? Would the inner shell be the position of highest potential, or the outer shell be the position of highest potential? Highest potential. Outer shell or inner shell? outer shell, right? Good. And if this electron happened to fall from this outer shell and move to this inner shell, what would have to happen in order to account for that energy difference? Because this is high potential, lots of energy up here. Low potential, not a lot of energy down here. So if this high energy electron drops to this low energy orbit, it has to lose some of its energy.
Right.
So what happens? If this were a ball rolling down a hill, the ball's at the top of the hill, rolls to the bottom of the hill. What kind of energy does the ball convert from what to what? It converted its potential to kinetic, but this isn't a regular ball, right? So this ball converts potential to electromagnetic potential, right? Photons of light. If this ball, electron, falls from a position of high potential to a position of low potential, it has lost potential energy. But we know better than that. We know energy is never lost. Energy converts, right? In the case of electrons, when electrons lose potential, I'm going to say this 100 times until we've got it locked in. When electrons lose potential energy, it's okay, we can just have me say it. When electrons lose potential energy, they emit photons equivalent in energy to how much energy they just lost, right? Let's get this back here. Hang on.